Quest at Manchester offers another useful personal insight. Karen. He found his programming team's missing schedules by about one half. Each job was taking approximately twice as long as estimated. The estimates were very careful, done by experienced teams estimating man hours for several hundred subtasks on a Berg chart. When the slippage pattern appeared, he asked them to keep careful daily logs of time usage. These showed that the estimating error could be entirely accounted for by the fact that his teams were only realizing 50% of a working week as actual programming and debugging time. Machine downtime, higher priority short unrelated jobs, meetings, paperwork, comp. 90 calling the shot. Baby business, sickness, personal time, etc. Accounted for the rest. In short, the estimates made an unrealistic assumption about the number of technical work hours per man year. My own experience quite confirms his conclusion. Registered. Karen's data. Joel Aaron, manager of systems technology at IBM in Gaithersburg, Maryland, has studied programmer productivity when working on 9 large systems briefly. Large means more than 25 programmers and 30,000 deliverable instructions. Aaron divides such systems according to interactions among programmers with system parts and finds productivity as follows. -4. Very few interactions, 10,000 instructions per man year, some interactions 5,000. Many interactions, 1,500. The man years do not include support and system test activities, only design and programming. When these figures are diluted by a factor of 2 to cover system tests, they closely match Hare's data. Hare's data. John Marr, manager of programming for the Bell Telephone Laboratories Electronic Switching System, reported his and others' experience in a paper at the 1969 Spring Point Computer Conference. Registered these data are shown in Fig. 8.2, 8.3, and 8.4. These. Figure 8.2 is the most detailed and the most useful. The first 2 jobs are basically control programs, the second 2 are basically language translators. Productivity is stated in terms of debug words per man year. This includes programming, component tests, and system tests. It is not clear how much of the planning effort or effort in machine support, writing, and the like is included. Here's data. 91. Figure 8.2 summary of 4 number 1 as program jobs. Productivities likewise fall into 2 classifications. Those for control programs are about 600 words per man year. Those for translators are about 2,200 words per man year. Note that all 4 programs are of similar size. The variation is in size of the work groups, length of time, and number of modules. Which is cause and which is effect. Did the control programs require more people because they were more complicated? Or did they require more modules and more man months because they were assigned more people? Did they take longer because of greater complexity or because more people were assigned? One can't be sure. Control programs were surely more complex. These uncertainties aside, the numbers describe the real productivities achieved on a large system using present-day programming techniques. As such, they are a real contribution. Figures 8.3 and 8.4 show simultaneously data on programming and debugging rates as compared to predicted rates. 92 calling the shot. March, June, September, December. Figure 8.3 as predicted in actual programming rates. Deck. March, June, September, December, March, June, September, December. Figure 8.4 as predicted in actual debugging rates. OS 360 data. IBM OS 360 experience, while not available in the detail of Hare's data, confirms it. Productivities in range of 600 to 800 debug instructions per man year were experienced by control program groups. Productivities in the 2,000 3,000 debug instructions per man year were achieved by language translator groups. These include planning done by the group, including component tests, system tests, and some support activities. They are comparable to Hare's data, so far as I can tell. Hare's data, and the OS 360 data all confirm striking differences in productivity related to the complexity and J difficulty of the task itself. My guideline in the morass of estimating complexity is that compilers are 3 times as bad as normal J-batch application programs and operating systems are 3 times as bad as compilers. Karen. Formado's data. Both Hare's data and OS 360 data are for assembly language programming. Little data seem to have been published on system programming productivity using higher level languages. Formado admits project Mac reports, however, a mean productivity of 1,200 lines of debug placed by statements per man year on the Multics system between 1 and 2 billion words. Karen. This number is very exciting. Like the other projects, Multics includes control programs and language translators. Like the others, it is producing a system programming product, tested and documented. The data seem to be comparable in terms of kind of effort included. And the productivity number is a good average between the control program and translator productivities of other projects. But Formado's number is lines per man year, not words. Each statement in his system corresponds to about 3 to 5 words of handwritten code. This suggests 2 important conclusions. 94 calling the shot. Productivity seems constant in terms of elementary statements, a conclusion that is reasonable in terms of the thought a statement requires and the errors it may include. Karen. Programming productivity may be increased as much as 5 times when a suitable high-level language is used. Karen. 4%. Karen W. 1. Height, T. 10 pounds. In a 5-pound sack. The author should gaze at Noah and learn, as they did in the art, to crowd a great deal of matter into a very small compass. Sydney Smith, Edinburgh Review. Engraved from a painting by David Marty, Method Archive. 97. Program space is cost. How big is it? Aside from running time, the space occupied by a program is a principal cost. This is true even for proprietary programs, where the user pays the author a fee that is essentially a share of the development cost. Consider the IBM APL interactive software system. It runs for $400 per month and, when used, takes at least 160 KB of memory. On a Model 165, memory rents for about $12 per kilobyte per month. If the program is available full-time, one pays $400 software rent and $1,920 memory rent for using the program. If one uses the APL system only 4 hours a day, costs are $400 software rent and $320 memory rent per month. One frequently hears horror expressed that a 2 MB machine may have 400K devoted to its operating system. This is as foolish as criticizing a Boeing 747 because it costs $27 million. One must also ask, what does it do? What does one get in ease of use and in performance via efficient system utilization for the dollars so spent? If the $4,800 per month thus invested in memory rental have been more fruitfully spent for other hardware, for programmers, for application programs. The system designer puts part of his total hardware resource into resident program memory when he thinks it will do more for the user in that form than his adders, disks, etc. To do otherwise would be grossly irresponsible, and the result must be just applications to set the sizes of the systems to be offered. Then these systems have to be subdivided, and each component given a size target. Since size-speed trade-offs come in rather big quantum jumps, setting size targets is a tricky business, requiring knowledge of the available trade-offs within each piece. The wise manager also saves himself a kitty to be allocated his work proceeds. In OS 360, even though all of this was done very carefully, still other lessons had to be painfully learned. First, setting size targets for core is not enough. One has to budget all aspects of size. In most previous operating systems residence had been on tape, and the long search times of tape meant that one was not tempted to use it casually to bring in program segments. OS 360 was disk resident, like its immediate predecessors, the Stretch operating system and the 1410-7010 disk operating system. Its builders rejoiced in the freedom of cheap disk accesses. The initial result was disastrous to performance. In setting core sizes for each component, we had not simultaneously set access budgets. As anyone with 20/20 hindsight would expect, a programmer who found his program sloshing over his core target broke it into overlays. This process in itself added to the total size and slowed execution down. Most seriously, our management control system neither measured nor caught this. Each man reported as to how much core he was using, and since he was within target, no one worried. Fortunately, there came a day early in the effort when the OS 360 performance simulator began to work. The first result indicated deep trouble. One ran H on a Model 65 with Grouse, simulated compiling at 5 statements per minute. Digging it showed that the control program modules were each making many disk accesses. Even high-frequency supervisor modules were making many trips to the versus Caradel, and the result was quite analogous to page crashing. The first moral is clear. Set total size budgets as well as resident space budgets. Set budgets on backing store accesses as well as on sizes. The next lesson was very similar. Space budgets were set before precise functional allocations were made to each module. As a result, any programmer in size trouble examined his code to see when he could throw over the fence into a neighbor's space. So buffers managed by the control program became part of the user space. More seriously, submit all kinds of control blocks, and the effect was utterly compromising to the security and protection of the system. So the second moral is also clear. Define exactly what a module must do when you specify how big it must be. The third and deeper lesson shows through these experiences. The project was large enough in management communication, or enough to prompt many members of the team to see themselves as contestants making brownie points rather than as builders making programming products. Each sub-optimized his piece to meet his targets, and he stopped to think about the total effect on the customer. This breakdown in orientation and communication is a major hazard for large projects. All during implementation, the system architects must maintain continual vigilance to ensure continued system integrity. Beyond this policing mechanism, however, lies the matter of attitude of the implementers themselves. Fostering a total system, user-oriented attitude may well be the most important function of the programming manager. Space techniques. No amount of space budgeting and control can make a program small. That requires invention and craftsmanship. Space techniques 101. Obviously, more function means more space, speed being held constant. So the first area of craftsmanship is in trading function for size. Here there comes an early and deep policy question. How much of that choice shall be reserved for the user? One can design a program with many optional features, each of which takes a little space. One can design a generator that will take an option gist and tailor a program fit. But for any particular set of options, a more monolithic program would take less space. It's rather like a car, with the map light, cigarette lighter, and clock are priced together as a single option. The package will cost less than if one can choose each separately. So the designer must decide how fine-grained the user choice of options will be. In designing a system for a range of memory sizes, another basic question arises. The limiting effect keeps the range of suitability from being made arbitrarily wide, even with fine-grained modularity of function. In the smallest system, most modules will be overlaid. A substantial part of the smallest system's resident space must be set aside as a transient or paging area into which other parts are fetched. The size of this determines the size of all modules. And breaking functions into small modules costs both performance and space. So a large system, which can afford a transient area 20 times as large, only saves accesses thereby. It still suffers in both speed and space because the module size is so small. This effect limits the maximum efficient system that can be generated from the modules of a small system. The second area of craftsmanship is space-time trade-offs. For a given function, the more space, the faster. This is true over an amazingly large range. It is this fact that makes it feasible to set space budgets. The manager can do two things to help his team make good space-time trade-offs. One is to ensure that they are trained in programming technique, not just left to rely on native code and previous experience. For a new language or machine, this is especially important. The peculiarities of its skillful use need to be 102 10 pounds in a 5-pound sack. Learned quickly and shared widely, perhaps with special prizes or praises for new techniques. The second is to recognize that programming has a technology and components need to be fabricated. Every project needs a notebook full of good subroutines or macros for queuing, searching, caching, and sorting. For each such function, the notebook should have at least 2 programs, including the squeeze. The development of such technology is an important realization task that can be done in parallel with system architecture. Representation is the essence of programming. Beyond craftsmanship lies invention, and it is here that lean, spare, fast programs are born. Almost always these are the result of stated breakthrough rather than tactical cleverness. Sometimes the strategic breakthrough will be a new algorithm, such as concluding to be fast Fourier transform or the substitution of an n-log n sort for an inherent set of comparisons. Much more often, strategic breakthrough will come from reviewing the representation of the data or tables. This is where the heart of the program lies. Show me your flowcharts and conceal your tables, and I shall continue to be mystified. Show me your tables, and I won't usually need your flowcharts, they'll be obvious. It is easy to multiply examples with the power of representations. I recall a young man undertaking to build an elaborate console interpreter for an IBM 650. He ended up packing it onto an incredibly small amount of space by building an interpreter for the interpreter, recognizing that human interactions are slow and infrequent when space was dear. Digitech's elegant little 4-grid compiler uses a very dense, specialized representation for the compiler code itself, so that external storage is not needed. conspire to define certain items of paperwork that a project must prepare. To the new manager, fresh from operating as a craftsman himself, they seem an unmitigated nuisance, an unnecessary distraction, and a white tide that threatens to engulf him. And indeed, most of them are exactly that. Bit by bit, however, he realized that a certain small set of these documents embodies and expresses much of his managerial work. Preparation of each one serves as a major occasion for focusing thought and crystallizing discussions that otherwise would wander endlessly. Its maintenance becomes his surveillance and warning mechanism. The document itself serves as a checklist, status control, and a database for his reporting. In order to see how this should work for a software project, let us examine the specific documents useful in other contexts and see if a generalization emerges. Documents for a computer product. Suppose one is building a machine. What are the critical documents? Objectives. This defines the need to be met and the goals, desiderata, constraints, and priorities. Specifications. This is a computer manual plus performance specifications. It is one of the first documents generated in proposing a new product and the last document finished. Schedule. Budget. Not merely a constraint, the budget is one of the manager's most useful documents. Existence of the budget forces technical decisions that otherwise would be avoided, and, more important, it forces and clarifies policy decisions. Organization chart. Space allocations. Documents for a university department 109. Estimate. Forecast. Prices. These three have cyclic interlocking, which determines the success or failure of the project. Forecast merit estimate. Prices. To generate a market forecast, one needs performance specifications and postulated prices. Quantities from the forecast combined with component counts from the design to determine the manufacturing cost estimate. They determine the per unit share of development and fixed costs. These costs in turn determine prices. If the prices are below those postulated, the Vuze success spiral begins. Forecasts rise, unit costs drop, and prices drop yet further. If the prices are above those postulated, the disastrous spiral begins, and all hands must struggle to break it. Performance must be squeezed up and new applications developed to support larger forecasts. Costs must be squeezed down to yield lower estimates. The stress of this cycle is a discipline that often evokes the best work of hardware and engineer. It can also bring about ridiculous vacillation. I recall a machine whose instruction counter popped in or out of memory every 6 months during a 3-year development cycle. At one phase, a little more performance would be wanted, so the instruction counter was implemented in transistors. At the next phase, cost reduction was the theme, so the counter would be implemented as a memory location. On another project, the best engineering manager I ever saw served often as a giant flywheel, his inertia damping the fluctuations that came from market and management people. Documents for a university department. In spite of the immense differences in purpose and